Greetings, everyone. My name is Emma Busch, and my advisor is Dr. Pierce, and my project is called It's Freezing Out There, Take My Sweater, examining how math can be enhanced by knitting in the case of freeze patterns. In my project, I look at the connection between math and knitting, specifically in the representation of symmetry and the freeze patterns. When we had to submit project proposals last spring, it was right after we had been sent home halfway through the semester, and one of the main things that had brought me joy and kept me energized was immersing myself in knitting projects. Thinking about what I wanted to be working on all of senior year felt daunting, but incorporating something I enjoyed and that allowed some creativity made me a lot more excited to begin working on my IS. So, as a brief introduction to group theory, a group is a set of elements with a binary operation. An example of this is the integers and the operation of addition. Every group must have an identity element, so in the case of the integers, this is the number 0, because 0 added to any number will simply return that number. So 0 plus 2 is 2, 0 plus 3 is 3, and so on. Finally, every element in a group must have an inverse element. In the integers, this is the relationship between the positive and negative integers, where 2 plus negative 2 and negative 2 plus 2 will give you the identity element 0. Looking specifically at freeze groups, we first must define what a rigid motion is. A rigid motion is any transformation on an object that preserves its shape, size, and orientation. So looking at the equilateral triangle on the right here, you can see that the vertices are moving around and being reflected and rotated, but the shape of the triangle remains the same. That's what a rigid motion does. So in the case of freeze groups, the possible rigid motions are translations, which is moving along in one direction, reflections, which is reflecting about a line, rotations, and glide reflections, which are a reflection followed by a translation. A symmetry group is a group made up of the possible rigid motions of an object, with the binary operation being the composition or combination of these transformations. So it could be a reflection and then a translation would be a potential combination. The word freeze comes from Greek architecture to define the section between the support beams and the roof with some sort of horizontal pattern. You can see this in the diagram on the right. And now the word freeze has been generalized to mean any pattern on a horizontal strip. A freeze group contains the transformations that create just that, a pattern repeating on a horizontal strip. In order to keep the movement horizontal, the rigid motions possible for a freeze pattern are restricted to translations to either the left or the right, vertical and horizontal reflections, and rotations of 180 degrees. Due to these restrictions, there are exactly 7 unique freeze groups, which are pictured in the diagram to the right, and demonstrated using the motif of footprints and named accordingly. So for example, F1, which is simply translating the motif of the foot to the right, is called a hop, and so on. The wallpaper groups are also a subset of symmetry groups, but they are less restricted than the freeze groups. The wallpaper groups can be extended in any direction rather than simply horizontal, and the one restriction on them is the crystallographic restriction, which limits the angle an object can be rotated by. Due to this restriction, there are exactly 17 wallpaper groups, with examples of a few on the right. This flowchart functions as a tool for classifying patterns into wallpaper groups. And to practice using this flowchart, we're going to use an example of a design to go through the flowchart and classify what kind of wallpaper group it is. So the design that we're going to use here is called Angels and Devils, and it's by MC Escher. And going back to the flowchart, the first question is, what is the largest rotation order? Looking at the pattern here, we can see that the design is being rotated by 90 degrees, which is a rotation of order 4. So back to the flowchart. And on the flowchart, we can follow that line from the 4 and see that the next question is there a reflection? So looking back at the design, we can see that the angels are being reflected across a horizontal axis, while the devils are being reflected across a vertical axis. So the answer to that is yes. And so following that line on the flowchart, the final question is, are there mirror lines intersecting at 45 degrees? And we already went over that the two reflections are horizontal and vertical, not at 45 degrees. So the answer is no. So this design is wallpaper group P4G. So finally, to look at the relationship between math and knitting, which is mutually beneficial, they benefit each other, and looking at the geometry of knitting. A knit stitch is made by taking a row of loops on one needle and adding a new row of loops that pass through the previous row of loops. And this is done by inserting the other needle through the back of the yarn, wrapping new yarn around it, and pulling through. And these stitches can be mapped as a sort of rectangular grid. And the ways of shaping this grid are by doing different stitch types and doing increases and decreases. So an increase is most commonly done by adding 2 new stitches to the same stitch. This is similar to mapping of X to 2X. And you can look at the picture here to see how an increase will actually affect the shape of the rectangular grid. And so similarly, a decrease is done by knitting 2 stitches together. This is like mapping X to 1/2 X. And using increases, decreases, and various types of stitches, knitting is the creation of a structure made through choices in the creation of each individual stitch. And this shows that knitting is a lot more technical and mathematical than one might think originally. So looking at knitting mathematical objects, an example on the right is a torus made by Sarah Marie Belcastro. And knitting mathematical objects on one hand can be very useful to help with visualizing and increasing understanding of a mathematical concept. Like a torus, for example, if you're graphing that on a computer and trying to visualize it, it can be a bit tricky to see a 3D object in 2 dimensions. But being able to craft one and to hold it and to rotate it around in your hands and really understand the shape of the object is an excellent tool for understanding a mathematical concept, such as the torus. One difficulty with knitting mathematical objects, there are some limitations to what you can do with knitting. So for example, knit stitches are not square. So when comparing a knit stitch grid to a coordinate grid, you might have to make your knit stitch graph paper into rectangles in order to get the shapes that you want instead of squares. The product that I chose to produce for my final product was a symmetry sampler. So a sampler in general in the field of the fiber arts is a product made up of a patchwork of various designs demonstrating different motifs and crafting skills. It was traditionally used as an instructional tool or a way to pass on a pattern within a community of knitters. And a symmetry sample in the field of the mathematical fiber arts is a product that expresses the relationship between an art form, in this case knitting, and a category of the symmetry types, so in this case the 7 frieze patterns. And the exactness of the symmetry depends on the chosen fiber art. So in this case for knitting, a typical technique for representing patterns in knitting is color work, usually done with stockinette stitch, which is knitting one side of the fabric while purling the other. And purling is done in a similar way to knitting, except for the other needle is going to the front side of the yarn instead of the back. And so on the knit side of the stockinette fabric, the knit stitches are forming these V shapes that you see in part A of the diagram, while on the other side, the purl stitches are forming bumps, as you can see on part B of the diagram. So typically a pattern with color work is done by carrying over the yarn and the colors you're not using on the purl side or the wrong side of the fabric, while the actual design that you're trying to create is displayed in the knit stitches. These V shapes of the knit stitches are problematic because while they have reflectional symmetry across a vertical line, they do not have horizontal reflectional symmetry or rotational symmetry. However, typically mathematical knitters will gloss over this and treat their pattern as a rectangular grid still, but also recognize that there are inherent flaws in their symmetry samplers due to the stockinette stitch. So like I said, for my physical knit product, I decided to make a symmetry sampler of the 7 frieze patterns in the form of a knitted sweater vest made up of a patchwork of rectangles featuring the frieze patterns. To create the designs, I first made a motif, which here is boxed in red, and then applied the desired frieze pattern transformations to it. The top one with the trees is P1, the pattern of simply translations, and the bottom one in purple is made up of 180-degree rotations. This pattern here is made up of reflections across the horizontal axis and functions as an example of the effects of the V shape of the knit stitch on the actual symmetry of the knit product. Here you can see when reflecting the motif over, the knit stitch is still a V in the same direction, so that is a flaw in the symmetry of the physical knit product. To conclude, here is the front and back of the sweater vest that I created with each patch of color representing one of the 7 frieze patterns. The process of designing the sweater while writing my thesis greatly increased my understanding of both knitting and math as I saw the concepts that I was writing about come to life in the vest. I'd like to thank my advisor, Dr. Pierce, for all her help and support this year, as well as my housemates, my Worcester family, and my family at home for all their encouragement. Here are all of my sources that I use for my paper, and feel free to ask any questions that you have in the comments. I got up here so that I could show that I'm wearing the sweater vest that I knitted with each of the patterns on it. But thank you for your time and for listening.